Voyager 1 probe, the most distant human-made object in the universe, is sending usable information to Earth.
Voyager 1 and 2 were these craft built and launched in the 70s.
Voyager 1, our enduring silent ambassador to the stars, has revealed something both astonishing and profound. As it drifts through interstellar space, it has detected a staggering 775 unknown objects passing by. This unexpected bounty of cosmic phenomena invites us into a realm where our understanding of the universe's complexity and content is both humbled and invigorated. Before we start, smash the like and subscribe buttons for more updates. Voyager 1's journey, launched in 1977, has steadily carried it beyond the solar system into the vast emptiness of interstellar space. Its instruments, though old, remain capable of capturing whispers of the cosmos that defy our expectations. The count of 775 unknown objects, unclassified, perhaps unimagined, speaks to the fact that even in regions thought sparse, the interstellar medium teems with surprises. This revelation, articulated by Neil deGrasse Tyson, sparks wonder about what these objects might be and what they say about the universe around us. Imagine the intense emptiness outside the heliosphere, the solar bubble where sunlight fades, and charged particles from our star no longer dominate the medium. Voyager 1 moves through this region, equipped with systems like the plasma wave subsystem, designed to measure fluctuations in charged particles and detect subtle radio emissions. These instruments likely picked up the traits that define these unknown objects. Anomalies in the electromagnetic environment that hint at physical presence, perhaps dense pulses, transient clusters, or radiation signatures unlike anything cataloged. Each detection is a fragment of a deeper cosmic story. Signals from the unknown whispering across the void. Consider what might constitute unknown objects in this context. Are they rogue asteroids? Fragments unmoored from their parent systems? Are they relics of dust or interstellar clouds, aggregations of matter drifting aimlessly through space? Could they be dense pockets of gas or dust, perhaps shaped by remnants of supernova shockwaves or interstellar turbulence? Alternate theories might even stretch the imagination. Primordial objects from the early universe, muted echoes of material that existed before star systems formed. Or maybe they are photograph lesions, unknown plasmas or electromagnetic phenomena we've mistaken for physical objects. The implications of such findings shake the foundation of our cosmic assumptions. For starters, the interstellar medium-ism may be far more heterogeneous than portrayed in textbooks. Instead of a diffuse, near-vacuum expanse, it may be shot through with small-scale structures, dense knots, drifting aggregates, and electromagnetic anomalies that have gone unnoticed because we lack the instruments or proximity to detect them. Voyager 1's detection of hundreds of such objects suggests we may have underestimated the patchiness and dynamic complexity of our galactic neighborhood. These insights cast fresh light on astrophysical modeling. If interstellar space is filled with objects of varied composition and behavior, our understanding of galactic evolution, star formation, and cosmic ray propagation must be adjusted. For example, star-forming regions may be influenced not just by grand-scale molecular clouds, but also by streams or swarms of drifting objects that perturb gravitational and magnetic environments. The movement of cosmic rays, high-energy particles traversing space, might be moderated or scattered by encounters with these objects. Even gravitational lensing, the bending of light by massive objects, could be subtly affected if these unknown bodies exert measurable influence. On a broader scale, this discovery re-energizes our quest to map and understand the universe. We often think of exploration as expansion, sending craft, probes, and satellites ever further. But here in our own cosmic backyard lies discovery in the unmapped and unexpected. It highlights that exploration is not only about distance, but about nuance, about paying attention to what was previously assumed to be empty. The unexpected finds of Voyager 1 remind us that the universe holds secrets not only at distant, exotic locales, but also within the immediate frontier of interstellar space. These 775 objects also open a philosophical doorway. What constitutes an object in the vastness of space? When the definition becomes ambiguous, when plasma waves, dust aggregations, electromagnetic irregularities appear as discrete items, our understanding of materiality and classification must adapt. The discovery beckons a reevaluation of how we define and categorize phenomena in the universe, pressing for new frameworks that embrace ambiguity and complexity. Voyager 1's sensors, answering decades of silence with this flood of new questions, also underscore the value of persistence in science. It reminds us that even aging technology, flying billions of miles from its origin, can still surprise us. The spacecraft's endurance has granted us a rare vantage, unchanged, relentless, tiny in size but monumental in impact. These detections may inspire new generations of missions designed to map the interstellar medium in fine detail or launch follow-up instruments to characterize these objects, probing their composition, behavior, and origins. Furthermore, the revelation invites us to ponder the cosmic choreography of motion. If these objects are drifting past, a journey of thousands, perhaps millions of years, then their trajectories intersecting with Voyager 1 at just this moment might illustrate a dynamic dance of interstellar debris and materials. Their fleeting passage reminds us that space is not static. It is alive with motion, with things traveling between star systems, influenced by gravitational waves, passing stars, and unseen forces. It suggests a universe in motion, where seemingly empty spaces are pathways for cosmic wanderers. This discovery also has a humbling emotional resonance. Voyager 1, a creation of human ingenuity, becomes a translator between the known and the unknown, revealing that knowledge is never complete. It reminds us of our cosmic smallness, but also our capability to detect, reflect, and imagine. The craft becomes a beacon of curiosity, carrying the dreams of exploration forward even as its power gently fades. At a time when discussions often swirl around grand future missions or rivalries to reach further into space, this finding refocuses attention inward, into that vast gap we call interstellar space. It whispers of fortunes waiting there, not in new planets or alien civilizations, but in humble, mysterious objects weaving through the void. These silent travelers may not capture headlines like exoplanets or black holes, but they speak in a subtle language, one of persistence, surprise, and the unknown. The timing of this revelation also casts a deliberate reflection. Voyager 1's power supply is diminishing, its radioisotope thermoelectric generator is slowly losing effectiveness. Soon, its instruments may go silent, its voice fading from interstellar space. That makes these detections even more precious, an evocative final gift from a pioneering spacecraft nearing the end of its mission. It is a reminder that scientific legacy is built across time, with wonders emerging unexpectedly even as an old explorer nears retirement. In essence, the detection of 775 unknown objects passing Voyager 1 invites us to reconsider the familiar emptiness of space. Rather than a quiet void, interstellar space may be more like a seascape, dotted with pieces of driftwood, shoals of unseen art, and currents we barely perceive. It invites renewed curiosity, deeper study, and a reimagining of the cosmic environment that surrounds us. It also evokes excitement for the scientific community. The findings could spur the development of new detection methods, refine instrumentation, and inspire missions specifically tasked with investigating these objects. Perhaps future probes will be outfitted with advanced imaging, mass spectrometers, or dust analyzers to capture close-up data, revealing whether these objects are lumps of complex material, icy remnants, dust agglomerates, or something entirely unexpected. Even for the public, these revelations thrill. Humanity has a deep-rooted fascination with the unseen. Ghosts of stars, dark matter, the interstellar drift. The idea that Voyager 1 encountered 775 unknown things out there captures imagination. It might reignite interest in space exploration, drawing attention not only to dramatic planets and galaxies, but also to the small, the obscure, the quiet puzzles that drift unseen. Understanding these objects also touches on planetary defense and astrobiology. If there are swarms of drifting objects in interstellar space, what might happen when such clouds intersect with emerging solar systems? Could they seed material, deliver organic compounds, or influence planetary formation? And in terms of protecting Earth, might long-range surveys benefit from accounting for unknown interstellar drift, space weather at a scale previously overlooked? In the grand tapestry of the cosmos, Voyager 1's revelation of 775 unknown objects is a single glittering thread, but it is one that changes the pattern. It suggests that we have more to learn in our own cosmic backyard than we ever thought. That interstellar space is rich with untold tales waiting for someone to listen. Engaging with this event stirs the spirit of exploration. It reminds us that the next breakthrough might come not from a telescope pointed at distant stars, but from an old spacecraft silently drifting, listening, and, at the right moment, revealing something completely unexpected. It urges us to look again at the void and to realize that the void might just be alive. Voyager 1's detection of 775 previously unknown objects drifting through the interstellar medium offers an opening to peer into a realm of physics and astrophysics that has rarely been experienced directly. The reality that such a large number of discrete signatures appeared in its data forces us to rethink the very architecture of the galaxy beyond our solar bubble. It's not simply that these objects are unexpected, it's that they appear in a zone we have long assumed to be sparse, almost sterile compared to the dynamic solar system we know so well. This changes the baseline assumptions that have guided generations of scientists in mapping the broader Milky Way. One of the most fascinating aspects of this discovery lies in the way it compels astronomers to examine the environment outside the heliosphere with new eyes. The heliosphere, inflated by the constant push of the solar wind, has long been thought of as a kind of protective shield. Beyond it, we imagined a comparatively uniform plasma, punctuated occasionally by denser molecular clouds or the remains of past stellar explosions. Yet the appearance of hundreds of unknown bodies challenges the notion that interstellar space is, in most places, smooth and homogeneous. Instead, what Voyager 1 has detected hints at a lumpy, unpredictable environment filled with microstructures that could play subtle but significant roles in shaping the galaxy's larger-scale dynamics. These objects could represent the detritus of ancient stellar systems, small, dense remnants that were ejected by gravitational interactions or disrupted planetary systems. Over billions of years, such ejections could populate interstellar space with a vast inventory of debris. Some of these pieces might be relatively large, comparable to asteroids or comets, while others could be smaller, yet still massive enough to disturb local plasma fields and magnetic lines. Voyager 1's sensors, though not equipped to photograph these entities, might be picking up the electromagnetic disturbances or particle interactions they cause as they pass nearby. If this is the case, then the sheer number Voyager 1 has identified could be the tip of an immense iceberg. We may be looking at a statistical clue that interstellar space is littered with countless objects, perhaps trillions, drifting between stars, completely invisible to our telescopes because they reflect little to no light. The only way we detect them is through the faint, indirect disturbances they cause in the surrounding environment. This could mean that the galaxy contains an enormous hidden population of free-floating material, quietly shaping the cosmic stage in ways we are only beginning to appreciate. The potential origins of these objects stretch our understanding across multiple disciplines. Some could be rogue planets, ejected from their home systems during early formation chaos or after close encounters with passing stars. Others could be frozen fragments from protoplanetary disks, leftovers from the birth of stars billions of years ago. Still others might be interstellar wanderers composed primarily of volatile ices, slowly eroding under the constant assault of cosmic rays. The diversity of potential compositions opens new questions about the chemistry and mineralogy of interstellar space. It's possible that many of these objects carry compounds or isotopic ratios not found in our solar system, offering clues to the galactic chemical evolution over cosmic time. The role of the galactic environment in moving these objects is another point of deep intrigue. Gravitational tides from the Milky Way's spiral arms, combined with encounters between stars and molecular clouds, could send these bodies on erratic journeys spanning tens of thousands of light years. Over time, such migration could mix material from vastly different parts of the galaxy. This galactic mixing might contribute to the spread of heavy elements and even organic precursors, dispersing the building blocks of planets and life far beyond their points of origin. Voyager 1's detection zone could therefore be a crossroads of material from multiple star systems, carrying with it the history of places humanity will never visit. The dynamics of these objects' motion through the interstellar medium are complex. Even at their relatively small sizes compared to planets, Their movement is influenced by the subtle drag of plasma, by interstellar magnetic fields, and by gravitational pulls from nearby stars. Some might be traveling at hundreds of kilometers per second, slingshotted by past gravitational interactions. Others may drift more slowly, their motion dictated by centuries-old perturbations. In some cases, they may form loose streams, families of objects sharing similar velocities and trajectories, originating from a common event such as the breakup of a larger body or the dissolution of a small stellar cluster. Such streams would be a fascinating target for future exploration. If Voyager 1's detections include such patterns, they could provide rare insights into the past events that shaped them. Analyzing these patterns could reveal not just the presence of the objects, but the story of their journeys across space. Understanding their kinematics might even allow scientists to trace some of them back to their points of origin, offering an unprecedented opportunity to map connections between distant star systems and the local interstellar neighborhood. This detection also pushes the limits of what we consider empty space from a navigational perspective. For decades, interstellar space travel has been conceptualized as a journey through near vacuum conditions, with hazards limited mostly to radiation and micrometeorites at densities far lower than those found in the solar system. But the discovery of hundreds of unknown objects within a small sample path changes that calculation. It raises questions about whether future interstellar missions will need more robust shielding against unexpected encounters with solid matter or dense particle clouds. The engineering requirements for high-speed interstellar probes could become more complex, as we learn that the void between stars is not quite as empty as assumed. From a purely observational standpoint, the methods by which Voyager 1 made these detections offer important lessons for future mission design. Its aging instruments are optimized for detecting electromagnetic and plasma signatures rather than direct imaging, yet they have proven invaluable in identifying the presence of otherwise invisible objects. This suggests that even without optical capabilities, spacecraft can make significant contributions to the mapping of interstellar structures. Future probes could be equipped with refined particle counters, magnetometers, and dust analyzers capable of detecting and characterizing such objects in far greater detail. The combination of direct and indirect observation could yield a much richer portrait of the space between the stars. The scientific importance of these findings extends beyond simple cataloging. Understanding the abundance and distribution of interstellar objects can directly influence our models of planet formation and system evolution. If such objects are common, they may play a role in transporting material between systems, potentially contributing to a kind of galactic recycling process. Over eons, this exchange could affect the composition of nascent planets and moons, shaping their atmospheres, crusts, and potential habitability. The implications for astrobiology are profound, as it raises the possibility that life's building blocks might not only arise locally within a planetary system, but could also arrive from interstellar space. Another dimension of this finding lies in the context of recent discoveries of interstellar visitors like Oumuamua and 2I/Borisov. These rare detections, made from within the solar system, already suggested that objects from outside our planetary family occasionally pass through our region. Voyager 1's much larger tally hints that such encounters could be far more frequent than we observe, simply because our detection methods are limited by distance and brightness. The spacecraft's vantage point beyond the solar wind's influence might make it more sensitive to these passers-by, catching them in the act of drifting through the galaxy's quieter corridors. The data also offer a potential testing ground for theories about dark matter and exotic astrophysical phenomena. While it is unlikely that these specific detections represent dark matter directly, their existence might help rule out or refine certain models that predict the density and distribution of mass in interstellar space. Moreover, studying how these objects interact with surrounding plasma and magnetic fields could shed light on poorly understood aspects of galactic magnetohydrodynamics, an area that influences everything from star formation rates to cosmic ray propagation. From a cultural and human perspective, there is a deep poetic resonance in the idea of hundreds of unknown travelers passing silently by a lone spacecraft launched by Earth nearly half a century ago. Each object has its own history, shaped by forces and events beyond anything in the human experience. Some might have been drifting for billions of years, bearing the chemical fingerprints of stars long extinguished. Others might be relatively young, products of recent cataclysms whose echoes have not yet reached our telescopes. To imagine them passing within detection range of Voyager 1 is to picture countless unrecorded stories unfolding in the darkness, momentarily illuminated by the briefest brush with human awareness. The detection also underscores the importance of sustained investment in long-term scientific missions. Voyager 1's continuing contributions remind us that exploration often yields its most surprising results well beyond the original mission parameters. What began as a mission to explore the outer planets has, decades later, transformed into an unprecedented survey of the interstellar frontier. It is a testament to the foresight of mission planners and engineers who built a spacecraft capable of enduring the harshest conditions and functioning far beyond its expected lifetime. If we extend our thoughts to the scale of the Milky Way, the implications grow even more staggering. Our galaxy contains hundreds of billions of stars, many with their own planetary systems. If each system produces even a small number of ejected bodies over its lifetime, the cumulative population of interstellar objects could be astronomical. Voyager 1's detections could thus represent not a local anomaly, but a common galactic feature, hinting that every cubic light-year of space may contain untold surprises. The diversity of these objects' possible compositions opens pathways for experimental science as well. If future missions can intercept such bodies, even in deep space, they could return samples that reveal entirely new chemistries. These could include isotopes formed under stellar conditions unlike those of our Sun, complex organic molecules synthesized in distant molecular clouds, or even exotic minerals formed under pressures and temperatures unknown in the solar system. Each sample would expand our planetary science beyond the confines of our own celestial neighborhood. In terms of cosmic safety, the findings introduce a layer of complexity to long-term planning for interstellar travel. Navigating through a medium populated with more solid material than previously assumed will require precise trajectory planning, real-time detection systems, and perhaps even deflection capabilities. The risks are not only to the structural integrity of spacecraft, but also to the success of sensitive scientific instruments that could be damaged by high-speed impacts with even microscopic particles. The discovery also enriches our understanding of the potential for panspermia, the hypothesis that life, or its building blocks, could travel between star systems on natural carriers. If interstellar space contains numerous solid bodies, some of which may have originated in life-bearing environments, then the chance that microorganisms or prebiotic compounds could survive long journeys increases. While this remains speculative, it ties into larger questions about the distribution of life in the galaxy and whether it might share common origins across distant worlds. As Voyager 1 continues its path outward, each new detection adds another data point to this unfolding picture of a galaxy alive with motion and mystery. The spacecraft's journey through interstellar space is like a slow drift through a vast, dark ocean, where occasional encounters with drifting ships or islands hint at an unseen geography. Mapping that geography will take more than a single probe. It will require a fleet of explorers designed to listen, sense, and sample the environment beyond the sun's influence. There is also a tantalizing possibility that some of these unknown objects are transient phenomena, short-lived formations of plasma or dust that coalesce under specific conditions and then disperse. Studying such events could provide rare experimental data on processes that are otherwise only modeled in simulations. Observations of their formation, stability, and dissipation could feed directly into our understanding of the life cycle of interstellar matter. The next logical step will be to cross-reference Voyager 1's detections with other instruments and missions. While no other spacecraft currently matches its position and capabilities, ground-based radio telescopes and space-based observatories could be tasked with searching for complementary signals. This collaborative approach could help determine whether the 775 detections represent a local cluster of interstellar debris, a passing stream from a distant source, or a more general property of the surrounding medium. What makes this moment particularly compelling is that it reflects the meeting of two very different scales: the vast, slow-moving theater of galactic processes and the precise, real-time measurements of a human-made instrument. Voyager 1 acts as a microscopic probe of a macroscopic system, capturing ephemeral details that hint at enormous underlying structures and histories. The balance between these scales, between the smallness of the probe and the enormity of its findings, is part of what gives this discovery its sense of wonder. If these objects could be visualized, perhaps through future spacecraft with imaging capabilities, they might reveal shapes and textures unlike anything we have seen. Some might be jagged and irregular, shaped by eons of slow erosion in the interstellar wind. Others could be smooth, coated in layers of frozen volatiles or metallic sheen. Still others might be cloaked in thin clouds of dust, blurring their outlines and making them resemble small comets in perpetual hibernation. Each would be a monument to the processes that created and transported it across unimaginable distances. In contemplating these objects, one is reminded that the boundaries we draw in space between solar system and interstellar medium, between one star's realm and another's, are artificial. Matter flows between these regions without regard for such lines, and Voyager 1 has become a witness to that ongoing exchange. The 775 detections are not just a curiosity. They are evidence of a dynamic galaxy where nothing is truly isolated and where even the smallest traveler has a part to play in the grand circulation of matter and energy. The setting in which these 775 detections occurred is unlike any environment humans have directly explored before. Beyond the heliopause, where the sun's influence fades into the greater galactic medium, conditions are governed not by a single dominant source of radiation or wind, but by the combined forces of many distant stars, diffuse plasma fields, and ancient shock waves from supernova. In this region, the density of particles is low compared to interplanetary space, yet the energy of the particles can be much higher, and magnetic fields twist and bend in unpredictable patterns. Any object traveling here is subjected to forces far subtler than the gravitational pulls that dominate within a solar system, and understanding those forces is crucial to interpreting what Voyager 1 has detected. The unique vantage point of Voyager 1 allows it to act almost like a buoy in an interstellar sea, sensing shifts in the currents around it. The disturbances attributed to these unknown objects may be the result of interactions between solid matter and the ambient plasma. When a moving body collides with charged particles in space, it can create wakes and shock fronts that ripple outward, leaving a detectable signature in radio frequencies or particle counts. The fact that hundreds of such events have been recorded in a relatively short span of time implies that either the local density of drifting material is much higher than anticipated, or that these objects are particularly efficient at producing detectable interactions. Both possibilities open up avenues for deeper study of how matter behaves outside the protective envelope of a star's influence. From a structural perspective, the makeup of these objects could influence the nature of the signals Voyager 1 perceives. Metallic-rich bodies, for instance, might interact with magnetic fields differently than porous icy conglomerates. A metallic surface could induce sharper electromagnetic variations, while a fluffy, low-density body might disperse particles in a broader, softer pattern. Without direct imaging or sampling, these distinctions remain speculative, but even the statistical differences in signal strength and duration could be analyzed to suggest broad categories of composition. This kind of classification would be the first step toward building a census of interstellar matter types. Another layer to this discovery is its potential to refine our understanding of the galactic neighborhood's topology. If the detections cluster in specific directions or appear to travel along similar paths, they could mark the edges of larger interstellar structures, such as the boundaries of local clouds or the remnants of ancient stellar associations. Mapping these pathways might reveal corridors through which material moves more freely, shaped by the interplay of magnetic fields and gravitational gradients. Such mapping would be invaluable for plotting future interstellar missions, not only to avoid hazards, but also to target regions where interesting or scientifically valuable material is most likely to be encountered. The scale of the discovery challenges the notion of isolation in deep space. Even at unimaginable distances from any planet or star, Voyager 1 has shown that encounters are not rare. The spacecraft's detections suggest that the galaxy is stitched together by a constant traffic of drifting bodies, slow messengers carrying the imprints of their origins. Each one, no matter how small, is part of a larger circulation of material that connects distant stellar systems into a unified, evolving whole. In that sense, this single data set from a solitary probe becomes a window into the galaxy's deeper rhythms, rhythms that will take generations of exploration to fully comprehend. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on Voyager 1 detecting 775 unknown objects? Predictions for discovery? We want to hear from you. Thank you for watching and see you next time.